Okay, getting ready 7. Again, we're working with differentiating between linear, exponential, and quadratic functions. Right? So there's 4 parts to each question. The first part is to tell whether or not the relation is a function at all. If it's not, you don't do anything else. You just quit after part A. Part B, we're going to then tell, since we said it was a function, we would say linear, exponential, quadratic, or neither one of those. If it is linear, exponential, or quadratic, we're going to identify what the first differences tell us. And then there's another part D, which changes from question to question, but expressing it in some other form. So, number 1, I had 81 freckles on my nose before I began using vanishing cream. After the first week, I had 27. So I went 81, 27. The next week I had 9, then 3, and so on. So is this a function? Well, if we put x values in there, 0, 1, 2, 3, yes, each week had one exact freckle number associated with it. So yes, this is a function. Is it linear, exponential, quadratic, or none of those? Well, I'm not sure if you knew these right away in your head, but if we could check from the back, 3 minus 9 is negative 6, 9 minus 27 is negative 18, so it's definitely not a linear arithmetic sequence. And 3 divided by 9 is 1/3, 9 divided by 27 is 1/3, so this one is exponential since it is multiplying by 1/3. Okay. Now, the first differences. In order to do those, we should really look at this in the form of a table. So 81, 27, 9, and 3. Our first differences here, 81 down to 27 goes down 54. 27 down to 9 goes down 18. And 9 down to 3 goes down 6. And what we see in those first differences are a common ratio of 1/3. So the first differences also show the same common ratio that the y values showed. In fact, there could be exponential functions. You will see one eventually, 1 or 2, that you don't see the common ratio when you look at the y values. You don't see it until you look at the first differences. Now, I've already set up my graph here with a scale and titles and labels. We need to make sure you choose a scale that will allow you to show all 4 points. So we've got to get all the way to 81. So I chose to count by 5s. Every box in the freckle axis is counting by 5s. Since I had 20 boxes to go across the x-axis, I did spread those out and I counted by 1/4. So every 4 boxes was 1 week. It's up to you as long as you can fit all 4 points. So the first point would be 0, 81. Second point, 1, 27. Next point, 2, 9. And then 3, 3. So that does show us the exponential curve that we would expect from this decreasing the common ratio 1/3. Okay, number 2, none of those x values in the table repeat, meaning every x value is paired with exactly one y value. So yes, this one is a function. To determine what type of function, we need to look for a pattern here. Well, this goes down 1/3, down another third, down another 1/3, and continues that way. So that makes this a linear function, and our first differences are constant. Okay, these blue numbers here are our first differences, and they are constant. In this case, negative 1/3. but the important thing to notice is they are constant. Write the explicit equation. Well, for a linear function, we know the explicit equation is y equals mx plus b form. So y is equal to my constant rate of change, negative 1/3, times x, plus the 0th term. Well, that is actually included in the table. It's 81. Number 3, this one does not pass the vertical line test. Almost every x value has more than one y value, so this one is not a function, so we do not bother answering parts B, C, or D. And number 4, we're looking at the speed of a baseball versus distance, and I labeled, because it wasn't really super clear which was which, the speed is the x value, the y value is the distance. So this one, we do see every one of the x values we are given has exactly one range value, so it is a function. Now it looks kind of linear, right? But we should check that to really make sure. So each of these x values goes up 5, right? So it's not counting by ones, but it is a constant difference in the x values. So that will help us in a few minutes. The 220 to 247 goes up 27. The 247 to 275 goes up, let's see, that's 25, 28. 275 to 304 goes up 29. 304 to 334 is up 30, then up 31. So it can't be a linear function because those differences, even though they are not counting by ones with the x values, it is a constant difference. So linear would have to have a constant change in the y values divided by a constant change in the x values. The x value change is constant. The y value is not. So can't be linear. It's not exponential because I'm not multiplying. I don't have a common ratio in any of those. This is the quadratic, our newest kind, because even though the x values aren't changing by 1, they are changing constantly, these difference of the y's are changing in a linear pattern. Okay, there's a linear pattern that it goes up by 1 every time. Those first differences are linear, that makes it quadratic. Now, we have also went ahead and looked at the second differences. This would be up 1, up 1. So remember, quadratic is either that the first differences are linear, which we see here, 27, 28, 29, 30, 31, or that the second differences are constant, which we see with a 1. So predict the distance the baseball flies if it leaves the bat at a speed of 115. Well, that's just the very next point following this pattern. So if we went to 115, up another 5 for the x values, we would this time go up 32 on the y values, so that would put us at 397. And that's not a rough estimate. According to this pattern, we should all predict exactly 397. All right, so now we are looking at different representations. We have explicit equations, recursive, we have scenarios, we have graphs, we have tables. We're going to decide linear, quadratic, or exponential. Number 5 is linear because we see the form mx plus b. So this is linear. Number 6 is exponential because the variable is in the exponent. So this makes it exponential. Number 7 is a parabola, which makes this one quadratic. Number 8, it looks linear at first glance. I should check here. So I'm going to look at my rise over run. we go down 2 boxes, right 1, down 2, right 1, down 2, right 1. So if we have that constant rate of change, that makes it linear. Number 9, we're gaining interest at 3%. Any change, any increase or decrease by a percent of your value is always exponential. That's exponential growth. Number 10, now this recursive looks a little different than we're used to. We usually say f of n equals f of n minus 1 plus 2n. But that's really exactly the same as what's here. Both of these mean to get your next value, you go back to the one right before that, the previous one. So what came right before f of n plus 1 would be f of n. If I write it the way we're used to, what comes right before f of n? F of n minus 1. So don't let that throw you off. It means exactly the same as the way we write it. So here's what I'm really looking at is what am I adding on each time or multiplying. So this time I am adding a linear expression. So if I am adding a linear expression every single time, that means my first differences are linear. So this is a quadratic. Okay? If this were a linear function overall, then there would just be a constant added here, a plus 2 or a plus 3 or a plus 7. But when we're adding a linear expression, that makes the whole function quadratic. Okay, notice in number 11, it says the area of the triangles, not just counting the base and the height as x and y, but looking at a pattern of the areas. So area here, I added the formula is 1/2 base times height. So for this first one, 1/2 times base times height. So that gives us an area of 2. Next one, 1/2 base times height gives us an area of 6. Third one, 1/2 base times height gives us 12. So what are we seeing as that increases? From 2 to 6 goes up 4. From 6 to 12 goes up 6. Now really, 3 numbers is not much of a pattern. We're really assuming a lot to say that this is what we see in those first couple is going to continue. But it's certainly not linear because it doesn't have a constant rate of change. It isn't multiplying since 2 times 3 is 6, but 6 times 2 is 12. It cannot be exponential. But we do see, if we look at these, we only have 2 first differences, 4 and 6, but that could be the beginning of a linear pattern. So the only one that we could choose out of, from what we see here, is quadratic. Okay, again, that's not a very good question. There should be at least one more example to see that next time it adds 8 and we get an area of 20. Okay, now, if we were ambitious, we could try that. If we look, each of these bases is increasing by 2. So our next triangle would have a base of 8, and each height goes up 1. So the next one would have a height of 5. So if we did the area formula there, 1/2 of 8 times 5 is 20. So it does add 8, and yes, this is a quadratic pattern. But be careful with only seeing 3 numbers and assuming that you know exactly what is going to continue to happen. All right, number 12, we want to put these in a form we can deal with. Point A here is 0, 5. B is 1, 3. C is 2, 1. And D is 3, -1. So we see in that pattern a constant rate of change. It goes down 2 each time. So that makes this linear. I know that looks like a line. So if you're asking, well, why do we have to even do the table? We can tell right away that it's a line. You should at least count the rise over run to identify slope, because sometimes if you're zeroed in on just a little piece of a parabola, it can look linear, like the one we saw yesterday with the baseball, the speed and the distance with the baseball. That looked linear, but turned out to be quadratic. All right, number 13, to get the next number, we do 2 times the last number. Definitely makes it exponential. Number 14 might not look like exactly what you're used to. Maybe you recognize it as a slightly reversed standard form of a linear equation. You could also subtract x from both sides and think of it as y equals negative x, so that it looks like slope-intercept form. But regardless, this is definitely a linear equation. There are no exponents. X and y are not multiplied. There's no variables in the denominator, so we're safe saying linear. 15, to get the next value, we go back to the last one and subtract 2. Again, that makes it linear. That's a constant rate of change. Number 16, each of these 2 expressions that are written here are linear. So when we have a linear times another linear expression, we've talked about that always results in a quadratic expression, quadratic equation. If you were to multiply this, you would, x times x does result in the x squared that we are used to seeing with a quadratic equation. Number 17. Now, since there doesn't seem to be any pattern to what we are seeing in either the x's or the y's, this one might be a little tricky, but if you look at the way the each x compares to its own y value, what did each one do? Well, to get each f of x or each y value, all we did was change the sign, change from either negative to positive or positive to negative. So the equation would simply be f of x is equal to the opposite of the x value. Well, hopefully when you see that simple equation, you can recognize that that's in slope-intercept form, so this is linear. And 18, since we have a 20 in the exponent there isn't an x value at all, but I'm kind of treating this as if we are substituting 20 for x here. This one looks exponential to me.